So in the last two videos, we were talking about this constrained optimization problem where we want to maximize a certain function on a certain set, the set of all points x, y, where x squared plus y squared equals 1. And we ended up working out through some nice geometrical reasoning that we need to solve this system of equations, so there's nothing left to do but to just solve the system of equations. We'll start with this first one at the top, see what we can simplify. We notice there's an x term in each one, so we'll go ahead and cancel those out, which is basically a way of saying we're assuming that x is not 0, and we can kind of return to that to see if x equals 0 could be a solution. So maybe we'll kind of write that down. We're assuming x is not equal to 0 in order to cancel out. And we kind of can revisit whether that could give us another possible solution later. But that will be 2 times y is equal to lambda times 2. From here, the 2's can cancel out. No worries about 2 equaling 0. And we know that y equals lambda. So that's a nice simplified form for this equation. And for this next equation, we can use what we just found, that y is equal to lambda, to replace the lambda that we see. And instead, if I replace this with a y, what I'm going to get is that x squared is equal to y times 2 times y. So that's 2 times y squared. And I'll leave it in that form because I see that in the next equation I see an x squared, I see a y squared, so it might be nice to be able to plug this guy right into it. So in that next equation, x squared, I'm going to go ahead and replace that with y squared. So that's 2y squared plus y squared equals 1. And then from there, simplifies to 3 times y squared equals 1, which in turn means y squared is equal to 1/3. And so y is equal to plus or minus the square root of 1/3. Great. So this gives us y, and I'll go ahead and put a box around that we have found what y must be. Now, if y squared is equal to 1/3, then when we look up here and we say, 2 times y squared, that's going to be the same thing as 2 times 1/3. So 2 times 1/3. So if x squared is equal to 2/3, what that implies is that x is equal to plus or minus the square root of 2/3. And then there we go. That's another one of the solutions. And I could write down what lambda is, right? And we can, in this case it's easy because y equals lambda. But all we really want in their final form are x and y, since that's going to give us the answer to the original constraint problem. So this gives us what we want, and we just have that pesky little possibility that x equals 0 to address. And for that, we can take a look and say, if x equals 0, let's go through the possibility that maybe that's one of the constraint solutions. Well, in this equation, that would make sense, since 2 times 0 would equal 0. In this equation, that would mean that we're setting 0 equal to lambda times 2 times y. Well, since lambda equals y, that would mean that for this side to equal 0, y would have to equal 0. So evidently, if it was the case that x equals 0, that would have to imply from the second equation that y equals 0. But if x and y both equal 0, this constraint can't be satisfied. So none of this is possible, so we never even had to worry about this to start with. But it's something you do need to check. Just every time you're dividing by a variable, you're basically assuming that it's not equal to 0. So this right here gives us 4 possible solutions, 4 possible values for x and y that satisfy this constraint and which potentially maximize this. And remember, when I say potentially maximize, the whole idea of this Lagrange multiplier is that we were looking for where there's a point of tangency between the contour lines. So just to make it explicit, the 4 points that we're dealing with, I'll write them all here. So x could be the square root of 2/3, square root of 2/3, and y could be the positive square root of 1/3. And then we can basically just toggle. Maybe x is the negative square root of 2/3, and y is still the positive square root of 1/3. Or maybe x is the positive square root of 2/3, and y is the negative square root of 1/3. Kind of monotonous, but just getting all of the different possibilities on the table here. X is negative square root of 2/3, and then y is negative, that's the last one, square root of 1/3. So these are the 4 points where the contour lines are tangent. And to find which one of these maximizes our function, here, let's go ahead and write down our function again. It gets easy to forget. So the whole thing we're doing is maximizing f of xy equals x squared times y. So let me just put that down again, we're looking at f of xy is equal to x squared times y. So we could just plug these values in and see which one of them is actually greatest. And the first thing to observe is x squared is always going to be positive. So if I plug in a negative value for y, right, if I plug in either this guy here or this guy here where the value for y is negative, the entire function would be negative. So I'm just going to say that neither of these can be the maximum because it'll be some positive number, some x squared times a negative. Whereas I know that these guys are going to produce a positive number. And specifically, if we plug in f of, let's say, this top one, square root of 2/3, square root of 1/3, well, x squared is going to be 2/3, and then y is square root of 1/3. And in fact, that's going to be the same as what we get plugging in this other value. So either one of these maximizes the function. It's got two different maximizing points, and each one of them has a maximum value of 2/3 times the square root of 1/3. And that's the final answer. But I do want to emphasize that the takeaway here is not the specific algebra that you work out going towards the end, but it's the whole idea of this Lagrange multiplier technique, to find the gradient of one function, find the gradient of the constraining function, and then set them proportional to each other. That's the key takeaway. And then the rest of it is just, making sure that we check our work and go through the minute details, which is important. It has its place. And coming up, I'll go through a few more examples.